Am I sharing the right screen?
Think so.
Okay, good. All right, so the Augmented Reality Nautilus Operations Center was born out of the complexity of that spaghetti monster trace route visualization that I showed. Let's see, there we go, there it is. So there's a lot of data available in this very, very simple flat map, but it's almost impossible to use because there's the user interface sucks. The the amount of data that's available is just minimal. It doesn't show you enough detail to actually solve anything. It just shows you where the problem is. It doesn't tell you what the problem is. And so we started storyboarding. How can we fix this? We wanted to create a persistent game that hosts all of our digital information with live visualizations that operate across platform at scale. And so that's at multiple scales: planetary, zooming in, regional, city, building, into the rack space, and right into the wiring. The tool we're developing for our cluster maintenance provides the crucial infrastructure for building out global XR scale experiences. So this is kind of an excuse to do a whole bunch of other things on top of what we're paid to do. And that's always fun. So here's some other storyboards. Here, the upper left is the US view. The upper right is the San Diego view. You may or may not recognize Atkinson Hall and the bear on the lower left. That's the building outside view. And then the lower right is in the data center view, where you see the racks and servers. And all along those same lines that you saw on the spaghetti monster have been pulled down into this view. So that same live data is available in all of these views. And that's very important. So we started doing internships several years ago. Our last one, Laminar Reality, was a very, very productive group of students, all undergrads. The pipeline we wanted to create is to display our K8S network Nautilus traffic data in a meaningful way to users through the use of virtual environments in the cloud. So what does that look like? Well, we have our pipeline has data. We started out using Houdini for doing effects processing, pushing those developed assets into Unreal Engine, and then using a Google Agonis open source game server engine to scale that out to a planetary multiplayer instance, and then the user. It's a little more complicated. We have Nautilus that has perf sonar and netbox running in it. We have all kinds of assets that we store, procedural models that are generated from architectural designs using Revit and AutoCAD designs. All those are stored in the cluster on the same devices that we're measuring with this tool. We're also using spatial anchors to associate devices that might be mobile or temporal into the game. And so these storyboards helped us work through the process. Now, these storyboards, I think, are maybe 2.5, 3 years old. And so we've gone through several of iterations. And so this was before that, the first betas that we were able to show. Everything we're doing, again, is stored in Netbox. Netbox is our start of truth. Here we can see the regions. This is an abstraction layer that we can extend to anywhere we want. I personally added the University of California as a region, and then inside of that are the sub-regions of all the University of California universities that are part of the Nautilus network. Inside of the sites, you can see instantly from this view, there are 7 racks, 54 devices, 36 prefixes, 54 VLANs available, and it has other information like you can store images and GPS physical addresses, GPS coordinates, all the contact information, time zones, all these things can be pulled from Netbox into Unreal to inform the visualization. It's very, very fast. One of the other things that you get per site is a topology map. So if you manually enter, I've connected this switch to this server using this wire and this port, it will draw this diagram for you automatically. We're working on Ansible scripts that reach out to all the physical nodes using LLDP, Link Layer Data Protocol, that will describe that automatically for us so we don't have to manually input all the cabling. It can be discovered and then documented in Netbox, and then all we have to do is pull this topology from the REST API into Unreal Engine, and we can render those devices into the racks with the right wiring. This is the rack elevations view. It gives us kind of a simple, hey, this server is in this rack at this slot. So Netbox knows where everything's at already. All we have to do is pull it out of its REST API. And so one of the other Netbox is open source and extensible. One of the other tools I put in there in the lower right side is a QR code. And so every rack will have a QR code on the top of the rack. And if you point your phone at that, it will link you directly to the Netbox page that we're looking at now. If you go into any device in that rack, each device will have the same QR code that can be printed out and stuck on the front panel of the device. The same with cables. You can put your QR code on your cable, and so you could just point your phone at it and you instantly identify what cable this is, what ports it's going to, and what the temperatures are on the optics in some cases. This is the overall topology viewer plugin. In the right-hand side, you see I have in the site ID, I've asked to display Atkinson Hall 1201 and the SCSC West Data Center. So I pulled up 2 data centers and can simultaneously view those. You notice they're not all connected. And that's because we haven't scraped all the information or manually entered it to populate all this. But we're getting really close on the automation, so we won't have to do this ever. This is what our beta app looked like. This is in Unreal. We're using a Bucky Fuller geoscope style of visualization where we're putting the data of the traces on the inside of the globe. Bucky's argument was if you're standing inside the globe, you can see more of the data. We also made the globe transparent, so that adds and subtracts to the visualization in some ways. On the right-hand bar on the side are your retransmits, throughput, packet loss, latency, MTU, and I forget the 5th one. And then the L1, 2, 3, 4, 5, those are the zoom layers. So these are just simple UI, UX things that we started out with. This is the global view, just a little animated so you can see the mouse over interactions. This is running in the game in the editor. We actually did push this game out to a HoloLens for some testing. And actually this is that HoloLens testing, which is not as exciting. This, however, is the most recent prototype from last week's meeting or 2 weeks ago's meeting. We're now here, we're using ArcGIS plugin for the globe, and we're now not doing the Bucky Fuller thing, but we're using splines that are automatically draped across the planet. And so we can add gravity, multi-body dynamics, so we can attract and repel. We can stretch the segments based on latency, and then we can overlay the color of the edge based on any metadata that we want, or decorate it with other flaming packets, whatever we want. This is a slide that was not in yesterday's deck also. This is a Geisel Library. This is part of our campus-wide photorealistic procedural generation for the AR knock. One of the things that we've done for Atkinson was we took AutoCAD drawings, which were as-built drawings that had complete detail of the building. Well, this building didn't come in AutoCAD. These are scans of physical drawings that were brought into AutoCAD and Revit, and we extracted a 3D photorealistic model from really old data, which is pretty cool. We're going to be advancing this model because it also works into our Rainbow's End Werner Vinge dreams of storytelling on campus. This is a shot from inside of the Geisel on the 6th floor. We do have the location of all of the shelves, the books, the stacks. So we're going to place those into the scene. And on the right-hand side, you can see this is in a Zoom session. These are our 11 people that were in the group at that time. This is a very, very diverse gang of people that have been picking at this problem for a few years. This is the Arcgis Map SDK that I mentioned. This is just a couple of months old. We're on the bleeding edge of geographic information systems in game engines. There's even more exciting things coming down in just later this month. This is on the left. You can see we're running the model in the Unreal Game Editor on a desktop, and on the right, this is in the HoloLens. I apologize for the alpha channel. It's an artifact of the screen capture thing that you can get with HoloLens. It just the viewer sees the model as it is in the left, but it just doesn't screen capture well. In here, this is our data center view where we have our servers in racks. And you also see these are log files from a node that was selected. Eventually, these will be floating windows that could be attached to any place in the room that you want. And so when you walk into the room, you don't have to pull up a physical console. You just throw a virtual console for that device that you're working on wherever you need it. And on the right-hand side, this is a non-traditional node. This is a Sun Cave. It's got 37 servers attached to it, 2 GPUs each. And we have to understand how it is connected physically and electrically. We use digital assets when we could get them. This is the Atkinson Hall. They came in as just slices. Each floor was a drawing when you use Revit to stack them. Datasmith to annotate. You can actually get all the metadata out of the drawing into the 3D model. And that's really important when it comes down to wiring Ethernet jacks in the building. And so actually, this is the same thing, but it's now running in Revit, which is just the tool that we use for building out the data, annotating it, and then pushing the model. We've improved the textures. That's one of the things you can swap out really easily. We just use kind of stock textures to start out with, but we're slowly swapping out real textures that we take from photographs. Eventually, we want to take point cloud and photogrammetry of the entire campus and overlay it as efficient textures. All right, let's see. Here we can see that we've pulled those into, yeah, this is Unreal, but we've also pulled through some Mapbox data. This came through the Houdini connection. We can pull Mapbox and OpenStreetMap data and then drop our models on top of that. What this means is you can get all the information from OpenStreetMap, like the location of every fire hydrant on the planet, or every telephone, or the center lines, or the sidewalk, curbs, and use those for stylizing your model. And here you can see kind of a breakdown of how we are creating the servers. These are the textures are kind of low res in this earlier version, but we created the Ethernet card that goes into the slot in the server. We created the blades that go into the slots in the switches. And then each one of those Ethernet jacks has an attachment for a cable or power or a console. So these are all, they're all considered actors in the game. And so you can have them move or attach or do other things. This is an example of procedural generation. This is, again, in Unreal Game. This is just pulling the data from Netbox. And as soon as you hit play, it pulls. And then right now, we're just working on how to label the racks, position the racks, and then stack the devices in the rack. And so this is just an exercise that they're doing to do debugging, where they scatter them across the floor so they're easier to read. And on this side, you can see that you can see the names of each server rack, the Suncave nodes, and eventually this will all be stacked into the rack in the right place. Let's see if I can get this to go. There we go. One of the other things that we've been doing a lot of is we're all working from home. Nobody can afford a $6,000 laptop that's capable of running Houdini and Unreal and all these high-end tools. So we started containerizing all these high-end graphics with this NoVNC tool that's been around for a bunch of years. But there's also some work that NVIDIA did, and we call our instance NoGL. And this is an example of NoGL. We're in a web browser, and we have GLX spheres running at 244 frames a second. At the same time, he's doing Unity. He's got Visual Studio running. He's got Houdini running. He's got Blender running, all at the same time, all in a web browser. You could also run multiple instances all at the same time, all in a web browser if you were really productive. We can also do pixel streaming. This is another service that's built into Unreal Engine. Basically, you can have a person that doesn't have a headset or a device that you can play on, or you can just log into the game just going in through a web browser. And so that's, again, it's a NoVNC wrapped instance. This is pretty low res because the guy was running too much on his instance to make this perform right. Parallel work we've been doing. This is, we've tested the NoGL, NoVNC on the Amazon Fire Stick, the NVIDIA Shield, Android 10 phones, iOS 10 phones, HoloLens 2, Oculus Go, and basically all OSs, Windows, Mac, CentOS, and Ubuntu.
But they're all just really just running the pixel stream, right?
Sorry, what was that?
None of these are running the application. They're just showing the display.
Correct. The application's running on the far end, but yeah, depending on what node you choose to run that application on, it may not be the best performing node. So like the Suncave nodes, they're just 1080 GPUs. So for a really big game, you're going to want a 2080 or 3080. So choosing your node is something that.
Right, but to reemphasize Jeff's point, the compute power to drive these simulations, whatever you want to call them, is on Nautilus, and the Amazon Fire is just the display device, correct? John, are you frozen?
With our instance here, we are fully connected to a CentOS version running completely on the server side.
That's my understanding, Lauren.
I have a full.
Okay, let's see. And then this is in the Amazon Fire Stick running Blender. John said this was the most enjoyable one. The latency was super low, and it was just amazingly good. We also have K3S, the Kubernetes for IoT cluster. You can see this is the Vroom space that CineGrid has done so many events in. What we're doing is we're taking 32 Google Edge TPUs, running TensorFlow on the TensorFlow accelerator from, these things are $100 each. The camera is like $24. And you run this PoseNet application, and basically anybody that walks in front of the camera instantly starts being tracked markerlessly. And so our goal was to take these 32 cameras and do the math and calculate the global position of every person in the room. Each one of these, if you have 4 people standing in front of one of these things, it will give you 4 people's poses. It'll also give you an accuracy measurement on each point in that pose, how accurate it thinks it is on determining that location. Then when you merge all those points and accuracies, you can determine which one has the best accuracy. So this must be this person in this spot. And then the really cool thing, we use a thing called VRPN, Virtual Reality Peripheral Network, to hook up all of our controllers for all of our game interfaces when we go into the Sun Cave. This will use the same interface. So it will be compatible with all kinds of other custom written code like CalVR and all the other tools from Oculus and Steam, and all the gadgets work. And so we'll just be adding yet another gadget. We also did a SIGGRAPH submission. I'm not sure. How are we on time for? Do you want to?
Well, we're about at time, John. So
Okay.
we're kind of into the Q&A period at this point.
Let me just go to this slide here. Sorry. So one of the other cool things that's a new plugin that NVIDIA released free. That's deep learning super sampling. Basically, this is using the tensor cores that are available in the RTX series GPUs from NVIDIA to do a deep learning neural network to calculate how to up-res and increase the frame rate and improve the shadow resolutions of your games dynamically on the fly. So basically, with it off, this scene is doing 42 frames a second. When you turn it on, it bumps up to 74 frames a second. This will work out really nicely for our extremely complicated photorealistic models that have all kinds of inputs. Hopefully this DLSS engine will decide what it needs to render at what resolution, so we can ignore all the stuff that it might be changing, but it's not changing enough to see. So this will make those decisions for us.